Inverse trigonometric functions, integration. In this section, we will learn how to integrate inverse trigonometric functions. In order to be able to integrate inverse trigonometric functions, we first need to remind ourselves how to complete square of a quadratic expression that we learned from our algebra class. Let's review it with a couple of examples. Let's complete the square of 3x squared minus 24x plus 35. Note that this is not an equation, so we cannot divide by 3. What you could do, though, is to factor out the 3 from the first two terms. So you can take it out 3, and you will have x squared minus 3 times 8 is 24, so you have 8x. And we will leave this 35 outside of the parentheses since it's not going to be the number that we need to complete the square. Now to complete the square inside of a parenthesis, we would need half of this number. We can ignore the sign for now since we're going to square it. So whether middle term is negative or positive, when you square it, it's going to become a positive number at the end. So I can ignore the sign for now and take the half of the number, which is 4, and then you need to square the number, which is 16. And now you are going to add a number here to complete the square. Then expression inside the parentheses become perfect square. However, what you just added is not positive 16 since it is going to be multiplied by 3. So what you really created is positive 48. And because you created a positive 48 that wasn't there before, you need to subtract that amount from outside of the expression so that positive 48 and negative 48 gives you 0. So you really haven't done anything to the problem. All we are doing is just manipulating in order to complete the square. So then 3 times the quantity x squared minus 8x plus 16 become perfect square of quantity x minus 4 square, and plus 35 minus 48 becomes negative 13. And now we're done completing square of the expression 3x squared minus 24x plus 35. Let's do one more. I've got 2x squared minus 10x plus 1. So again, this time, we will like to factor out the 2 from the first two term. So I have 2 times quantity x squared minus 5x, and I'm going to leave the constant outside of a parenthesis since it's not going to be helpful. Again, I'm going to need half of this number. Half of 5 is just 5 over 2. And I need to square this number, which is 25 over 4. And I need to add that number inside of a parenthesis to complete the square. So I'm going to add 25 over 4 inside of a parenthesis. However, that's going to be multiplied by 2. So what I really created is 2 times 25 over 4, which is 25 over 2, since 2 and 4 cancel. Since I created a positive 25 over 2 that wasn't there before, I need to subtract that amount from outside of the parentheses so that it is effect of adding 0 to the expression. Now I'm almost done. When I complete square, the expression become 2 times quantity x squared minus 5x plus 25 over 4 is quantity x minus 5 over 2 square. And when I compute positive 1 minus 25 over 2, that is positive 2 over 2 minus 25 over 2, which is negative 23 over 2. And now we're done completing square of the expression, 2x squared minus 10x plus 1. Okay, I think we are ready now. Let's do integrals of inverse trig functions. Let u equal g of x and du equal g prime of x dx, and let a be the constant. And if we have the form integral of du over radical quantity a squared minus u squared, that will be equal to arc sine of u over a plus c. If you have integral of the form du over quantity a squared plus u squared, that's going to result in 1 over a arc tangent of u over a plus constant of integration c. If you have integral of the form du over u times square root of quantity u squared minus a squared, that's going to be equal to 1 over a arc secant of absolute value of u over a plus c. So of course we're going to have to memorize this formula. But for number 5 test, I think I'm going to give you these 3 formulas. But for the final exam, you are going to have to memorize it. Okay? So here we go. Let's do some example. I have integral of 3x squared over 4 plus x to the 6 dx. So this is not u. We're probably going to have to do u sub. But knowing that there's no radicals in the denominator, I think it's going to be arctangent. So let's see if we can find the u du to see if it's in the category. So my u then has to be x to the third power, so that u square become x to the third to the second, which is x to the sixth power, which I have it right there. Then my du is going to be equal to 3x squared dx, which I have it right there. So if I change this, this is going to be equal to 3x squared dx becomes my du, and 4 is 2 square plus u square. So I do have integral of the form du over a squared plus u squared. So then, according to formula, it's a 1 over a, and my a is equal to 2, since 4 is 2 square. So I have 1 over 2 arc tangent of u. My u is x to the third power over a, my a was 2, plus constant of integration c. So I found my answer. Not bad, huh? If you know the formula, it's really easy. Next example, integral of 1 over x radical quantity x to the fourth power minus 9 dx. Which formula do you think we should use? Well, we got a variable outside of a radical, and also inside of a radical, we have function square, we got a variable square, minus number square. It looks like arcsecant to me. So we're gonna try to see if it is arcsecant. So if it is arcsecant, our u has to be x squared, so that u squared become x squared square, which is x to the fourth. But then du is going to be equal to 2x dx. But I do not have a 2x on the numerator, so I'm gonna need to manipulate a little. So I'm going to then multiply top and bottom of this integral by 2x over 2x, so that I would have 2x dx, which will give me du. So then I do have now integral of 2x dx, which I can turn into du now. And I multiply 2x times x in the front of radical, I get 2x squared. Radical x to the fourth is x squared square minus 3 square. So I'm almost close. Since x squared is my u, I have now u radical u squared minus a squared. So only thing this is different from our arcsecant formula is the 2 in front of my x squared. But 2 is 1 over 2, and it is the constant multiple. So I have no problem pulling out in front of integral. So I'm going to pull out 1/2 integral of, let's now convert it to u du. So 2x dx is my du, and x squared is my u, and x squared is again u square minus 3 square. So my a is 3. So now it perfectly fits my formula of arcsecant. I do have 1/2 constant multiple in front of integral, and integral of du over u radical u squared minus 3 squared is now 1 over a, and my a is 3. So it is 1 over 3 arcsecant of absolute value of u, and my u is x squared. And because x squared is a positive, I do not need to have absolute value, right? Because x squared is always greater than or equal to 0. So I will have x squared over my a is 3 plus constant of integration c. So final answer will be 1 over 6 arcsecant of x squared over 3 plus c. Next question. Integral of dx over quantity 2x squared minus 8x plus 10. Which of the inverse trig function integration should we use for this integral? It doesn't look like anything what we've been learning, isn't it? But one thing for sure is that there is no radical. So if it is one of those that we learned in the formula, it has to be arctangent. Oh, didn't we had to review how to complete square? So this is where we have to complete the square. Now, first off, with the 2x squared minus 8x plus 10, we can factor out the 2, right? So we can rewrite that as 2 times quantity x squared minus 4x plus 5, so that we can pull out the 1/2 in front of the integral. We can now rewrite this as 1/2 the integral dx over x squared minus 4x plus 5. And then, as we learned earlier, we are going to make this to 1/2 integral of dx over, let's complete the square. If you are more comfortable doing on the side, There's nothing wrong with that. You can do it on the side. You have x squared minus the 4x plus 5. We are going to put first two terms inside of a parentheses, and then we're going to leave constant term outside of a parentheses. And then we are going to take a half of the middle term, half of 4, which is 2, and then you are going to square the number, which is 4, and then you are going to add the number inside the parentheses, right? So you are going to add this number inside of a parentheses, and because there is no number outside of a parentheses, nothing's going to be distributed to the 4 that I just created. What you really created is indeed a positive 4. So you will like to undo the number from outside of a parenthesis so that you have effect of adding 0 to the original expression. So then this completes the square, and this becomes quantity x minus 2 square, and then when you compute positive 5 minus 4, you get positive 1. So your denominator, quantity x squared minus 4x plus 5, can be replaced by this expression right here that we just got by completing square, which is quantity x minus 2 square plus 1. So now we can call that to be our u. Our u is x minus 2, so that u square is x minus 2 square, which is what we have. And du is just dx. And then our a square will be 1, which makes our a equal 1. Then our u substitution becomes 1/2 integral of our du is dx over u square plus 1 square. Now our integral fits to arctangent formula. Wait a minute. We have arctangent formula as du over a squared plus u squared. Well, a squared plus u squared is the same as u squared plus a squared because addition is commutative. However, subtraction is not commutative. So with the arc sine and the arc secant, a squared minus u squared is not equal to u squared minus a squared. So we gotta be careful. But with the arctangent, it's okay for denominator to be either a squared plus u squared or u squared plus a squared. Okay, so now I had a 1/2 in front of integral times 1 over a, my a is 1, arctangent of u, my u is x minus 2 over 1 plus constant of integration c. When I clean it up, 1/2 times 1 is just 1/2. Arctangent of x minus 2 over 1 is x minus 2 plus c. So here is our answer. Next question. Integral 3 over 2 radical x times quantity 1 plus x dx. Here, I don't have really anything else to call u other than radical x. So I'm gonna try it. So let's call u equal radical x. Then my u square will be radical x squared, which is an x. And because u equal radical x is x to the 1/2 power, du is equal to 1/2 x to the negative 1/2 power dx, which is equal to 1 over 2 times x to the positive 1/2 power dx, which is equal to 1 over 2 radical x dx. And you can see I do have a du in the problem. I do have a 1 over 2 radical x dx. You're right. I do have a 3 over, but that 3 is a constant multiple. So I can always pull that out in the front. So let's do that. I have a 3 times the integral of 1 over 2 radical x and 1 plus x dx. So then 3 integral 1 over 2 radical x dx. Together it makes it du. And my x is, as you can see, u square. So you can interpret the 1 as a 1 square. So now I have arctangent formula right there. And my a square would be 1, and that makes my a 1. So according to formula now, my answer is, I do have a constant multiple 3 in the front, so I'm going to have 3 times. And 1 over a, and a is 1, arctangent of u over a, and a is 1, plus c. Now 3 times 1 is 3. Arctangent of my u was radical x plus c. So we got there. Our final solution is 3 times arctangent of radical x plus c. Next, a couple questions could be a little bit tricky. However, once you learn how to do this, you can definitely do this no problem. So here we go. Integral of 2x over quantity x squared plus 10x plus 29 dx. If you look at this problem carefully, your denominator is polynomial of degree 2, and your numerator is 1 degree less than that, which is degree 1. In this case, you want this to be 1 over u du, because then integral of that would be ln absolute value of u plus c. So let's see if we can pull that out. So if my u was the denominator, which is x squared plus 10x plus 29, what would it be my du? Derivative of that would be 2x plus 10 dx. Do you have that? Not quite. You have a 2x, but you don't have a 2x plus 10. So then, here is the trick you could do. Do the effect of adding 0. What you are going to do is, to this integral, you are going to add 10 and then subtract 10. What happened when you add 10 and subtract 10? Right, that's a 0. So you haven't done anything to the problem, right? No changes to a problem. These two expressions are exactly the same because 2x plus 10 minus 10 is 2x on the numerator. However, now I could separate this integral as 2x plus 10 over x squared plus 10x plus 29 dx minus integral of 10 over x squared plus 10x plus 29 dx. So now, as we set it with the green, you have an integral of, what's 2x plus 10 dx? You have it right there with the green set up. It is your du over quantity x squared plus 10x plus 29 is your u. What's the integral of du over u? Or 1 over u du? Yes, that is ln absolute value of u. And then we're going to continue now with second integral. You can see the denominator, you could complete the square. So if you complete the square, I have a 10. And let me complete the square on the side. So if I have x squared plus 10x plus 29, you can have a first 2 in the parentheses plus 29, leave it outside of a parenthesis since that might not be the number you want. And what is the number you need next to 10x in order to complete square? It's a half of 10, which is 5, and you want to square the 5, which is 25. So you need 25 here in order to complete square. And since there's a nothing in front of a parenthesis, there's a nothing to be distributed to 25. So purely you created a positive 25 that was not there before. So you need to subtract 25 outside of the parenthesis to compensate that. Then now you're almost done with completing square, and this expression is equal to x plus 5 square, and plus 29 minus 25 is plus 4. So my denominator can be rewritten as parentheses x plus 5 parentheses square plus 4, and 4 is 2 square dx. Have you seen something like that before? Yes, that's arctangent formula, except we have a 10 on the numerator. But 10 on the numerator, no problem, right? We can pull out the 10 on the numerator, and now I have 1 over x plus 5 square plus 2 square dx. Now I want to substitute what the u was because the integral next to it is different one and it will not be the same u. So let's go ahead and plug back what the u was in the first integral. I have a ln absolute value of u, and here my u was quantity x squared plus 10x plus 29. But as you just saw, x squared plus 10x plus 29, when you complete square, it is x plus 5 quantity square plus 4. So no matter what the x is, when you add the 5 and square it, it's gonna be greater than equal to 0. And when you add the 4 to it, this is always gonna be greater than equal to 4. So this quantity here is always positive. So you would not need absolute value. So you are going to just write as ln parentheses x squared plus 10x plus 29 minus 10 integral. Now here, my u is different u now. So let me change the color. So here, my another u is quantity x plus 5. So my du is then just dx. And then my a square is 4, which makes my a equal 2. So now I have 1 over u squared plus 2 squared du. So then, according to the formula, since I have an arctangent formula, my final answer is equal to ln parentheses x squared plus 10x plus 29 minus 10 times 1 over a, and my a is 2, arctangent of u over a is 2, plus c. So my final answer is, one more time, ln quantity x squared plus 10x plus 29. Negative 10 times 1/2 is negative 5. Arctangent. My u was x plus 5 over 2 plus c. So here is my final answer to this problem. All right, next question. Let's do this one without even having the formula this time. I got integral of quantity 3x cubed minus 2 over quantity x squared plus 4 dx. Wow, we have not seen something like this before either, huh? So if you have degree of a numerator greater than the degree of the denominator, then please do the long division and rewrite this quotient as the quotient of long division plus the remainder over the divisor. And once you do, rewrite this rational expression. So let's go ahead and do the long division. My dividend is the numerator, 3x cubed minus 2. But since it has a bunch of a missing term, I'm going to call that 0x squared plus, I'm missing also x term, so I'm going to call that 0x minus 2 divided by, my divisor is x squared plus 4. So x squared times what is 3x to the third power? That would be 3x. So when you multiply, you get 3x to the third power. You multiply positive 4 times 3x, you get plus 12x. So now you write under the like terms. We need to subtract top polynomial minus the bottom polynomial. That means switching the signs of a bottom polynomial to its opposite and add the top and bottom. So this first term's gone now, and you can carry the top ones down. You have a 0x squared, and then you have 0x minus 12x, which is negative 12x. And then you can bring it down the negative 2. But 0x squared is really 0. So you do not need that. So I'm going to erase that. All right? Now you can see I cannot divide no more because my remainder is degree less than the degree of divisor. Then we stop. So now we can rewrite this integral as integral of, what is this quotient? It is the quotient 3x, quotient of the long division, and then my remainder is negative 12x minus 2. So you can think that as a pulling out the negative in the front of a fraction. So now they both turn into positive because this negative supposedly distribute and it become negative 12x minus 2. Do you see that? So it's going to be minus 12x plus 2. So be careful with the sign over original divisor, which is x squared plus 4 dx. Very good. So now, integral of 3x is very easy because that's the integral of a polynomial. So go ahead and do that. What is the integral of 3x? That's a 3 over 2x squared minus, all I have to do is now integrate 12x plus 2 over x squared plus 4 dx. Wait a minute. My denominator is degree 2 and my numerator is degree 1. And I think we just learned from a problem before, if we have degree of numerator is 1 degree less than the degree of denominator, we are hoping that this would be integral of du over u, so that the result would be ln of absolute value of u plus c. So let's see if we could do that. Let u be x squared plus 4. Then my du is 2x dx. But I got 12x plus 2. Since I do not need that 2, I only need that 12x. Because 12x, I can make that as a 6 times 2x. So let's separate this again. Let's make this 3 over 2x squared minus integral of 12x. I'm going to make it 6 times 2x. That's a 12x over x squared plus 4 dx. And then I still have a 2, but this minus is also applied to that guy. Remember, this was a negative 2. So then that would be negative 2 integral of, I'm going to pull that 2 out, 1 over x squared plus 4 dx. Because this also, I think it looks like arctangent, isn't it? So now let's apply this blue u du to the middle integral. So then I have 3 over 2x squared minus 6 times. Now 2x dx is du over x squared plus 4 is u minus 2 times the integral of 1 over x squared plus 2 squared dx. Then this is equal to 3 over 2x squared minus 6 times. This was ln absolute value of u, but my u is right here, and since x squared is greater than or equal to 0, plus 4 will be always greater than or equal to 4, so my u is always positive, so I can drop the absolute value and say this is ln of quantity x squared plus 4 minus 2 times, if you look at that, that is 1 over x squared plus a squared dx, which is the arctangent with a 2. And we don't need the u there because we just have an x squared. So this will be equal to 1 over a times arctangent of x over a, and a is 2, plus c. So therefore, our final answer is 3 over 2x squared minus 6 ln quantity x squared plus 4. Negative 2 times 1 half, 2's get canceled. I have a negative arctangent of x over 2 plus c is my final answer to this problem. Woohoo! Last question, guys. Integral of x over radical quantity 5 minus x to the power 4 dx. All right. This kind of looked like arcsine to me because arcsecant has another variable in front of a square root. Arcsine was du over square root of a squared minus u squared. So let's see if this is the arcsine. So if this was arcsine, u squared was x to the power 4, then u must be x squared, right? So that if I square both sides, I get u squared and I get x to the power 4. Do you see that? Then du would be equal to 2x dx. No problem. I see x dx on the numerator. So all I have to do is multiply by 2 and divide by 2 so that I would have a 2x dx. No problem. And my a squared is 5. That would make my a radical 5. All right, no problem. We're almost there already. This one's an easy one, huh? So here we go. This is integral of, I need to multiply x by 2, and I need to divide by 2 so that I would have a 2x dx, which is my du. And I have a square root of radical 5 square minus x square square. So that now this is equal to 1 over 2 Integral 2x dx is my du over radical. I have a square minus u square. And now 1/2 times arc sine formula is no number in the front. It was just arc sine. And I have u over a plus c, which is equal to 1/2 arc sine. What was my u? My u is x squared over, what's my a? My a is radical 5 plus c. And that's it, guys. We're already done. This was too simple compared to what we've been doing, huh? So here is my final solution. 1/2 arc sine x squared over radical 5 plus c. All right, guys, we're done with last section. Congratulations, you're done with whole chapter 5. Thank you so much. You guys did a great job.